Hello, everybody. Welcome back. Excuse me. It has been a hot minute. Hold on. Okay, audio is working. All right, it looks like we are recording. Hello, everyone, and welcome back to more tutorials. It has been a hot minute since we did one of these. I'm sorry about that. I've been away with friends for the past week, basically. So, yeah, apologies. Let's get back into what we were up to. So, just a quick refresher as to what we've been doing. We are going through the book, Neural Networks from Scratch in Python, by Centdex, the YouTuber. We've been going through his book, which you can see on the left over here, which is in Python, Neural Networks from Scratch in Python, NNFS in Python. We've been going through that book, but we've been doing it in Golang, which is an awesome language made by Google. Personally, my favorite language. I'm in love with it right now. Although recently I've been feeling the pull back to Python, I'll admit, but I'm still in love with Golang. I really like the speed that it has. I really like the syntax that it has. So that's what we've been doing. It's been a fun project, and it's been going very well. It's been really nice. Just a quick, I say this in the beginning of every single thing, you can buy the book. There's a link to the book in the description, or you could just go to nnfs.io and you'll find the book, their website over here. Very cheap book, especially if you buy the ebook, PDF, which is what I got a few years ago when it came out. Love the book. Excellent, excellent, excellent. Highly recommend. You'll learn a ton. We can actually get rid of all of this, I believe. That is all obsolete. Highly recommend the book. Excellent, excellent book. So let's talk about what we've been doing. In the last tutorial, we moved things over. We made our dense layer struct. So I have my machine learning package over here, and we made our dense layer struct, which gets in the amount of neural inputs that it's going to take in, the amount of neurons that it'll have. It sets everything up with its weights, and it sets up biases to, the weights are initialized as random, the biases are initialized to 0. And then we set up the forward pass, which gets the dot product. All of this we discussed in previous videos. You can see the playlist down below. Highly recommend checking those out to get, you know, a feeling of where we're at. Additionally, then after we made this struct, we went back into the main.go file, and we turned our dense layers into these structs. So here we have a new layer dense with 2 neurons, with 2 inputs and 3 neurons, and then the second one is going to be 3 inputs, obviously, because from the 3 neurons over here, and then a 2 output, and then we do the forward pass between the x for the first dense layer, and then the forward pass for the second dense layer with the dense 1's output, and then we print out the dense 2 output. So let's just actually print what we have right now. Let's do go run everything. Let's see what we get. We get these beautiful, like a whole bunch. It's many outputs, many, a lot, because we have a lot of data. We got this data in a few, I think 2 videos ago. We got all this data. The x and y's, a lot of coordinates on a plane. You can check that out. Additionally, we plotted the data. This is what it looks like. You have these 3 classes in a spiral. So that's where we're at right now. This is actually a very important video, this one right here. In this video, we are going to learn about activation functions. Activation functions are a crucial concept to understand. How do I get rid of this, please? Dang it. Activation functions are why am I here? Activation functions are a crucial concept to understand. They are really what breathes life into neural networks. What makes neural networks so powerful really is the activation functions that you use. And so we're going to talk about in this video what they are, why we use them, how we use them, and we're going to make a very simple one. There won't be a lot of code. There's going to be a lot of reading in this one, so I highly recommend buying the book to follow along, or you could just follow along with my terrible reading because I'm going to be skipping a lot. So let me zoom in here, since the focus really will be on the book today, and the code is going to take like a little bit of a backseat for a while. So let's get right into it. Activation functions. Chapter 4. In this chapter, we will tackle a few of the activation functions and discuss their roles. We use different activation functions for different cases, and understanding how they work can help you properly pick which one of them is best for your task. The activation function is applied to the output of a neuron, or layer of neurons, which modifies outputs. So basically, when we have a neuron, when we have a layer, we have this dense layer, it has 3 neurons in it, so there'll be an activation function applied to the output of each of those neurons, and that activation function, like all functions, will take in the output, do something weird with it, and spit it back out, and the weirdness will actually be a very important tool that we use. Hold on a second, I'm going to turn on the air conditioning. It is very hot in this room. Thank you. Okay, now let's get back into it. Sorry, the air conditioning will probably make a noise because it's a little broken, so apologies for that, but anyway, onward. So yeah, so exactly, the activation function will take in the neuron's output and do something with it, and then output that. And yeah, it's important. So we use activation functions because if the activation function itself is nonlinear, it allows for neural networks with usually 2 or more hidden layers to map nonlinear functions. So let me explain the sentence over here. Why do we use activation functions? Is basically what this is explaining. So we'll talk about why, but for now, take my word for it that without a activation function, or really a specific kind of activation function, the neural network that you have, if it has 2 hidden layers, will only ever output a linear relation. So if you pass in inputs to this neural network, you'll only get a linear thing out. It can't map circular data, or if you have multiple dimensions, even more complicated than that. For example, the data that we have, hold on, how do I get it? The data that we have is clearly non-linear. This is clearly non-linear data. It's in a circle, and our neural network is going to have to figure out a way to map this. And it's going to need certain activation functions, because without those activation functions, it can only map a linear relation. And so everything above would be in one class, and everything below would be in another class. And you can only get like a line going through it. So you really do need these activation functions. And I'll explain why this is the case, but that is... Well, I'll explain why it is, or the book will explain why it is, that an activation function is essential to get a nonlinear relation. But for now, that is why we use activation functions. We use activation functions to get nonlinear relations from our neural networks. From our neural networks with 2 hidden layers, as he says over here, 2 or more hidden layers, to map nonlinear functions. So we're trying to map a nonlinear function, so we need these activation functions. Crucially, to keep in mind, he says very clearly, if the activation function itself is nonlinear, it allows for this. In other words, if you use a linear activation function, that's not going to work. What is a linear activation function? A linear activation function is a line. So a linear activation function would look like this. F of x equals 1/2 of x. That's a linear activation function. That returns a line. That's not going to work. A nonlinear activation function looks like this. F of x equals x squared. Right? That's not a line. That's going to be a parabola. So it needs to be a nonlinear activation function to get this effect that I'm talking about. We'll be showing how this works in this chapter. Great. In general, your neural network will have 2 types of activation function. There will be 2 types of activation functions in your neural network. The first will be the activation function used in hidden layers. That will be one kind. And the second will be the activation used in the output layer. So the output layer will almost always have a different activation function because the output layer needs to return a specific kind of number. And sometimes the numbers need to relate to each other, and so you'll get a sense of this. I think maybe in the next video we'll talk about the output layer's activation function. Usually the activation function used for hidden neurons will be the same for all of them, but it doesn't have to be. So you could use many activation functions for your hidden layers, but usually you don't. There's no reason to or not to. If you find a good activation function, it's probably good, and you'll use that. Okay, so let's talk about some activation functions that could be used. Recall the purpose of, the step activation function. Let's talk about this one. Recall the purpose this activation function serves is to mimic a neuron firing or not firing. So I don't know if this is a recollection, but let's declare this. The point of an activation function is to give us some data more dynamic than just this. Wait, the purpose, right, okay, sorry, hold on. The step function is a very simple function. It basically turns our neuron into, I don't care what data you're giving me, just are you firing or are you not firing? So that's what the step function does, and it achieves this effect, specifically the step function, it achieves this effect by simply saying that if the output from the neuron is above 0, return 1. If the output from the neuron is less than or equal to 0, just return 0. The simplest version, based on input information. So this is a very simple activation function. In a single neuron, if the weights times inputs plus biases, this is the output. If the weights times the inputs plus the biases results in a value higher than 0, the neuron will fire and it will give an output of 1. Otherwise, it will be an output of 0. So that's the step function. Very simple. This activation function has been used historically in hidden layers, but nowadays it's really it is rarely a choice. People don't really use the step function activation function. The step function activation function. The reason is because it gives you like no information. So this neuron could be returning a value of 10 billion, and you'll get a 1 back. It could also be returning a value of 0.00001, and you'll get a 1 back. So you lose a lot of nuance, and you don't want that. It's very important to have nuance when you're creating your neural networks, and so that's really why the step function activation function. I did it again. That's why the step function, the step activation function, there we go, is not used. The step function activation function. Is that what I keep saying? The step function activation function? Okay. I guess it's a good way of saying it. It's the step function activation function. All right. Now we have the linear activation function. A linear activation function is simply a line. It will appear as a straight line when graphed, where y equals x and the output value equals the input. So this is the simplest line you could possibly draw, y equals x. Depending on whatever x you put in, you'll get the y back. But a linear activation function would apply, like I said, to y equals 1/2 of x, y equals 2x, y equals 10 million, x plus 30. These are all lines. They're not really useful. This activation function is usually applied to the last layer's output in the case of a regression model. The truth is, this is nothing. Like y equals x is literally nothing. You are getting back the exact input that you're putting in. Sometimes you want to use a linear activation function in the last layer in the cases of regression. Linear regression, you want a line, obviously. A model that outputs a scalar value instead of a classification. So when you want just a straight up value, when the number is important, you'll tend to use a linear activation function of some kind. But if you're trying to do classification like we're doing, we are concerned with, in our actual example that we've been looking at, we are concerned with classes. So we have these 3 classes, and we basically want our neuron to receive a coordinate, an xy coordinate, and tell us what class it's in. So that's a classification situation. And so because of that, we would probably not be using a linear activation function on the output layer. You don't really want to use a linear activation function on the hidden layers because, like I said, the point of the activation function is to get a non-linear output. If you're using a line, you're not going to get a non-linear output. Okay, so there you go. Those were the first 2. These are the simplest ones. They're also the least useful. Sorry. Now we get to the one that was used for a ton of time. Now we get to a really, really widely used, and it was much more widely used in the past, activation function, the sigmoid activation function. If you know anything about machine learning, you may have heard of the sigmoid activation function. Okay, so let's take a look at this. The problem with the step function is that it's not very informative. Like I said, you lose a ton of nuance. When we get to training and network optimizers, you'll see that the way the optimizer works is by assessing the individual impact that weights and biases have on a network's output. So let's simplify that statement. When we're optimizing our neural network, when we're training it, what the optimizer does is it says, okay, we're wrong. Like, we got the wrong answer. Why? And so it looks at every single neuron and says, what did you do? Like, what kind of impact did you have on this wrong answer so that I know how much to tweak you? Now, if a neuron is outputting a value of 10 million, it means that it's having a big impact, right? But with the step function, all the optimizer will see is that it's outputting a value of 1 because it's going through the step function. So you lose a lot of information. Great. So the problem with the step function is that it's less clear to the optimizer what these impacts are because there's very little information gathered from this function. On the other hand, by the way, if the optimizer ignores the activation function and only looks at the neuron's output, it's going to think that the neuron is way more important than it is. Because it will see that the neuron is outputting a value of 10 million, and it'll be like, wow, you're having a big input. But it's not. It's like the neural network as a whole only sees that neuron as a 1, because the step function is only returning a 1. So it's really, it's honestly a bad function. Like, you should not use that function. There's no reason to. It's either on, 1, or off, 0. It's hard to tell how close this step function was to achieving, or how close this function was to activating or deactivating. Like, if it's 0.1, it activated, but we don't know how close it was to activating, because all we know is that it activated. Maybe it was very close, maybe it was very far. In terms of the final output value from the neuron, it doesn't from the network, it doesn't matter if it was close to outputting something else. Thus, when it comes to time to optimize weights and biases, it's easier for the optimizer if we have an activation function that's a more that are more granular and informative, that keep nuance. The original, more granular activation function used for neural networks was the sigmoid activation function, which looks like this. So notice, this actually kind of looks like a step function. Like, it really does. Here, this is a step function. The sigmoid kind of only just curves up. So the sigmoid activation function does 2 things, really. It curves up, and also it never gets to 1, and it never gets to 0. Like, the limit as x approaches infinity of the sigmoid activation function would be 1. But but it never actually gets there. We have this, what's it called? I forget what it's called. But whatever, the point is we never actually get to 1 using the sigmoid activation function. We never get to 0. That way you always keep nuance. The output from the sigmoid activation function for a value of 10 million will be different than the output for a value of 1. How different? It won't actually be that different, but it will be different, and you'll keep that nuance, and the optimizer will see that nuance, and it will be important. So this is what the sigmoid activation function is. It's 1 over 1 plus e to the negative x. There you go. That's it. And that spits out this beautiful shape, the S shape, basically. It looks kind of like an S, maybe. Kind of, maybe. Okay. This function returns a value in the range of 0, for negative infinity, through 0.5 for the input of 0, and to 1 for positive infinity. We'll talk about this function more in chapter 16. So the beautiful thing about this is that for a value of 0, it returns a 0.5, which is right in the middle, which is great. We want that. It returns it between a range of 0 and 1, but it never actually gets there. You just need infinity to get there. And we'll talk about this more in chapter 16, but it's a great function, not great. It's a great function, not as good as some others. So let's talk about why it's great in his words. I already mentioned a little bit, but we'll talk about it more. As mentioned earlier, with dead neurons, it's usually better to have a more granular approach for the hidden neuron activation functions. In this case, we're getting a value that can be reserved to its original value, reversed to its original value. So basically, with the step function, if the output is 0, the optimizer has no idea whether or not the input was negative 10 million or if it was negative 0.1, right? With this function, the optimizer will know. Like, it can actually reverse this. There is an inverse to this function because it's continuous. It's a continuous function, and it has a very clear inverse. And because of that, the optimizer will be able to understand things. The return value contains all the information from the input, contrary to a function like the step function. Where an input of 3 will output the same value as an input of 300,000, like I said. The output from the sigmoid activation function, being in a range of 0 to 1, also works better with neural networks. So we actually like values between 0 and 1 with neural networks, especially compared to the range of the negative to positive infinity, especially compared to the range of negative to positive infinity. I think he's talking about why it's better than linear, because linear will give you a range between like negative infinity and positive infinity, which we don't want. We want it to be between 0 and 1. We do like that. It's nice. And it also adds non-linearity. So you could think of it think about it this way. If there's a non-linear part to an activation function, it means you could use it to model non-linear data. So these curves in the sigmoid activation function, we can use those curves to model non-linear data, and it's very useful, as opposed to the linear activation function, which you got no curves. It's not curved. It's flat. It's not useful. Don't take that out of context. Okay. The importance of nonlinearity will become clear shortly in this chapter. Okay, so he's going to explain, and we'll see why nonlinearity is very important. The sigmoid function historically used in hidden layers. So the sigmoid function was very popular in hidden layers. It was eventually replaced by the king of all kings, the rectified linear units activation function. I just always call it rectified linear. I didn't know that it had a third part of its name. The rectified linear units activation function, ReLU. That said, we'll be using sigmoid function in the output layers activation function in chapter 16. So we will be using sigmoid in the activation function for the output layer, but now let's talk about the king of all kings, the simple but beautiful, the rectified linear activation function. Here we go. This is a very simple thing, as you can see. If x is greater than 0, return x. If x is less than 0 or equal to 0, return 0. The rectified linear activation function is simpler than sigmoid. It is quite literally y equals x clipped at 0 from the negative side. So it's just a very simple thing. If x is less than or equal to 0, then y is 0. Otherwise, y is equal to 0. So what was great? What was great? Let's think about it. What was great about the linear activation function? I know that I hated on it, but what was great about it? It's simple. You pass in an x, you get the same thing. It's very simple. There's no math involved. It's very clean, very little computation time, very nice. As opposed to 1 divided by 1 plus e to the negative x. That is a crazy function. The x is an exponent. You got e involved. There's a division happening. It's ridiculous. That is an intensively computational process. So the rectified linear kind of has the best of both worlds. It's very simple, very clean. X is just, y is just x, but not if x is less than 0. And also this little bend, all you need is that little bend, and now you can model nonlinear data. That's all you need. What is the downside of it? You have a range between 0 and infinity. That's the downside. I'll admit that it does have a downside in that sense. Okay, this is simple yet powerful this simple yet powerful activation function is the most widely used activation function at the time of writing for various reasons, mainly speed and efficiency. While the sigmoid activation function isn't the most complicated, it's still much more challenging to compute than the ReLU activation function. The ReLU activation function is extremely close to being a linear activation function while remaining nonlinear due to that bend after 0. This simple property, however, is very effective. This simple property is, however, very effective. Great. Okay, there you go. That was a brief rundown. You got the step function, not very useful. The linear activation function, not very useful. The sigmoid activation function, very useful, very pretty. I really like how it looks. Not ideal, kind of challenging to compute. And then we have the king of all kings at the time of making this video and at the time of writing this book, apparently, which was a few years ago, the rectified linear activation function. Okay, now let's talk about why. Like, I know I know I mentioned it, but why do let's really get the intuition why we use activation functions. Now that we understand what activation functions represent, by the way, if until now you've struggled with activation functions and you don't really know what they are and why they're there, if you've used like TensorFlow or PyTorch and you don't really understand what's going on, it's that simple. Like, was this complicated? It wasn't that complicated. These are the functions and this is how they work. Now let's talk about why they work and why we use them. It's amazing how simple deep learning is when you could just learn it. There's a lot of complicated ideas like shapes and stuff that kind of confuse you, but when broken down, they're actually super simple. All right, let's talk about why we use activation functions. That said, don't be embarrassed if you don't understand it. Go back and watch this again, watch some other videos, but I promise you it will click and you'll understand it and you'll be very happy. All right, onward. Now that we understand what activation functions represent, how some of them look, and what they return, let's discuss why we use activation functions in the first place. In most cases, for a neural network to fit a nonlinear function, we need it to contain two or more hidden layers, and we need those hidden layers to use a nonlinear activation function. So, real quick, if you have one hidden layer, you're going to get linear output. That's it. That's just how it goes. You need two or more to get nonlinear, and we'll see actually why, and we'll actually watch an animation why. Not made by me, made by the author of the book. Very helpful animation. But so you need more than one hidden layer, and you need activation functions. First off, what is a nonlinear function? A nonlinear function cannot be represented well by a straight line, such as a sine function. This is a nonlinear function. As you can see, it is not linear, not nonlinear. Also x squared, x cubed, x to the fourth, all these, what are they, quadratics? I have no idea. So yeah, these are all nonlinear stuff. Additionally, what's it called? Exponentials. E to the x is nonlinear. Okay. Also logarithms, which are the inverse of exponentials. Square roots, which are the inverse of, squares. Anyway, right, these are all nonlinear. While there are certain problems in life that are linear in nature, for example, trying to figure out the cost of some number of shirts, that is a linear function. The more shirts you have, the more money it will cost, and it's completely linear. You could represent that with a straight line. And we know the cost of an individual shirt and that there are no bulk discounts, then the equation to calculate, and there are no bulk discounts. That's important. If there's a bulk discount, in other words, as you buy more shirts, you actually, the amount that it costs, the amount that you're additionally being charged per shirt goes down. So if you buy two shirts, that's different. If you buy two shirts at once, it will be different than if you buy one shirt and then one shirt. That means that the slope of the line is decreasing, and so you're getting a non-linear situation. But if there are no bulk discounts, then the equation to calculate the price of any number of those products is a linear equation. So there are some problems in life that are straight up linear. Other problems in life are not that simple. And the problem is, those are problems that are very important when they're not linear. Like the price of a home. The number of factors that come into play, such as size, location, time of year, attempting to sell, number of rooms, yard, neighborhood, and so on, make the pricing of a home a non-linear equation. And actually, neural networks would be a great tool to get the price of a home, the proper price of a home. Additionally, prices to chairs and planes is nonlinear. There are a lot of factors there too, and we do, in fact, many companies do use neural networks to determine the price of a given chair in an airplane, believe it or not. Okay, many of the more interesting and hard problems of our time are nonlinear. The main attraction for neural networks has to do with their ability to solve nonlinear problems. First, let's consider a situation where neurons have no activation function, which would be the same as having an activation function y equals x. So again, a linear activation function is the same as no. No, that's not true. Hold on. Y equals x as an activation function is the same as having no activation function. A linear activation function could be different than having no activation function. For example, 1/2 of x is different than having no activation function, but it's almost just as useful. It's like useless. With this linear activation function, so again, it's a linear activation function, in the neural network with 2 hidden layers of 8 neurons each, the result of training this model would look like this. So this is the red line trying to approximate the value of the sine function. It does not have a good activation function. It has a linear activation function. It has 2 hidden layers, each one of them with 8 neurons. So it's getting in one input, which is the x. It's passing it through these 2 hidden layers, 8 by 8. Sorry, this one is 8, this one is 8, and then it's putting out one output, which is supposed to be the y, and this is just a disaster. Like, that was terrible. I mean, it's better than nothing. It's not that much better than nothing. Okay. When using the same, okay, so now this is with a what's called linear activation function. So now let's take a look at something else. When using the same 2 hidden layers of 8 neurons each, so we haven't changed anything, with the rectified linear activation function, we see the following result after training. This is a very beautiful mapping. And the reason why it's so jagged, by the way, is because of the amount of inputs that you're putting in. If you put in more inputs, it would be much smoother, because you get to have a lot more bends. The more neurons you have, the more bending you get to make use of. And again, all these bends are simply, like, they exist because of this bend here. Now, I don't want you to think that because this bend over here is sharp, that's why all these bends over here are sharp. It is kind of true, but if you have enough neurons, you won't be able to notice these bends. And they'll be smooth. They can be as smooth as you want. Trust me. Okay, so it's pretty cool. ReLU activation function in hidden layers attempting to fit y equals sine of x. Yeah, and you get this beautiful thing. Okay, now let's take a look at some real math involved. Where's the animation? I thought there was an animation. I don't know. Maybe there's an animation. So let's take a look at some of the real math. Let's get numbers involved. Linear activation functions and hidden layers. Now that you can see that this is the case, and maybe you don't have the proper intuition for it yet, but I encourage you, in fact, go down in the description. There's a link to his tutorial where if I don't show the animation in my video, it's in his video. It's an excellent animation. Watch his video on activation functions. Very, very useful. Or you can continue watching mine. Okay, now that you can see that this is the case, I'm just saying that the more you watch, the more you consume, the more intuition you'll get, and intuition is key. Now that you can see that this is the case, we should consider why this is the case. To begin, let's revisit the linear activation function y equals x. Let's consider this on a singular neuron level. Given values for weights and biases, what would the output be for a neuron with a y equals x activation function? Let's look at some examples. First, let's try to update the first weight with a positive value. Okay, so let's take a look at this. This is our neuron. Here we have a bias of 0. We have weight of 1, 0, 0. The input is 1, 2, and -3. And the output is 1. Why is the output 1? Well, let's take a look. 1 times 1 is 1, 2 times 0 is 0, 3 times 0 is 0, so 1 times 1 is 1, plus 0 is 1, so it's outputting a 1, and with a linear activation function of y equals x, the final output will also be a 1, because it's just, what's the x, then that's what the y is, and there you go. So you get this little dot over here, and you see this as a line. As we continue to tweak with weights, updating with negative numbers this time, so let's take a look over here now, it'll be negative numbers. So all that we changed is the weight over here, everything else is the same. Now we have a -1, and it's just a -1, it's still following on this line. And updating weights and additionally a bias, so now let's change the weights and the biases, and we still have it just straight up on this line. We have -3 times 1 plus 2, because these are all 0. So -3 times 1 plus 2 is -1, and you get this -1 over here. So as you can see, they're all always on this line. There's no output that will not be on this line for this neuron. Now, no matter what we do with this neuron's weights and biases, the output of this neuron will be perfectly linear to y equals x of the activation function. This linear nature will continue throughout the entire network. So every single neuron over here has a linear activation function, and so all of these neurons will be straight up on whatever line that they're working with. No matter what we do, however many layers we have, this neuron can only depict linear relationships. If we use linear activation functions, it should be fairly obvious that this will be the case, as each neuron in each layer acts linearly, so the entire network is a linear function as well. If every single component, you could think of a neural network really as a massive function that basically trains itself. Now let me ask you something. If every single part, if every single part of this function is linear, the function as a whole is also going to be linear. I wonder if there are different, like I wonder if some neurons have an input of like 1, of like y equals x, and some neurons have a, sorry, not an input, if some neurons had a function of y equals x, and some neurons had a function of y equals half of x, so they have different lines. I wonder if that would return nonlinear data. My assumption is no, because still everything is just linear. And so if each component is a linear relationship, then the function as a whole is just it's just gonna return a linear relationship between the inputs and the outputs. And so you won't be able to map anything. You won't be able to visualize any data other than in a linear in a linear fashion. So that's the tragedy of using a linear activation function. Now let's turn to our savior, our messiah, as it were, the ReLU activation in pairs of neurons. So let's take a look at the ReLU activation function. We believe it is less obvious how with a barely nonlinear activation function like the rectified linear activation function, it is almost completely linear, right? It only has that little bend. We can suddenly map nonlinear relationships and functions, and all of them as we want. We can map any nonlinear relationship that we want. So now let's cover that. Let's take a look. Let's start again with a single neuron. We'll begin with both a weight of 0 and a bias of 0. So here we have just 0, 0. It should be fairly obvious that no matter what goes in here, the output is going to be 0. And so the final output will be 0 as well. In this case, no matter what input we pass in, the output of the neuron will always be 0 because it has a weight of 0 and there's no bias. Let's set the weight to be 1. So now whatever we pass in will be the same. And so here we have a beautiful, simple, rectified linear. Whatever we pass in will be passed out because it's being multiplied by 1 and there's no bias. And so once it's passed out, it will go into the rectified linear activation function. And no matter what x we pass in here, if it's above 0, it will return that value. It will return y as that x value. And if it's below 0, it will simply return 0. Okay, so here we have a single. Okay, very good. Now it looks just like the basic rectified linear function. No surprises yet. So everything is the same. Now let's set the bias to 0.5. What does setting the bias to 0.5 do? It essentially shifts the entire output. Okay. So we can see that in this case with a single neuron, the bias offsets the overall function's activation point horizontally. By increasing the bias, we're making this neuron activate earlier. What happens when we negate the weight to be negative 1? But I want to talk about this for a second here. Okay, let's talk about what happens if x, the thing being passed into this neuron, is let's say 1. The thing being passed into this neuron, an x of 1. So 1 times 1 is 2. Is 1. And then 1 plus 0.5 is 1.5. And so it will fall like right over here, and so it'll return that. What if the input is 0? What happens if the input is 0? So if the input is 0, then this will be 0. 0 plus 0.5 will be 0.5, and then 0 plus 0.5 will be 0.5, and therefore therefore 0.5 is being passed in. Sorry, hold on. Hold on. I'm getting myself confused here. If this thing takes in a 0, then that means it will return a 0.5, right? So you can imagine this entire thing as that. This entire thing is a rectified linear function. Sorry. So if you pass in a 0 over here, you'll get 0 plus 0.5, which is 0.5. Is 0.5 greater than 0? Yes. So it returns 0.5. So when you pass in a 0, it returns 0.5. That's interesting. In this case, if you passed in a 0, it would return 0. The final product would be 0. That's interesting. So simply by offsetting the bias, we offset the entire firing point. The neuron fires earlier. It fires at lower values than it otherwise would have. Now if we flip, now if we flip the weight to be negative 1.0, if the weight is negative 1.0, then the entire thing flips. Isn't that beautiful? The entire thing flips. And so you can imagine, let's imagine that you have two layers, and these two were next to each other. You would have a graph that looks kind of like this, up, down, and like that, right? These things could make like a triangle if you organize them properly, right? And so that's the kind of relationship we're talking about here, and it's very interesting. But yeah, so it's very cool that if it's a negative 1 in the weight, it flips the entire thing, and you could almost see how we could use every neuron can now become a piece of the puzzle to mapping any kind of wavy function that we have. This neuron could map like this kind of part, and we could use this neuron to map everything from like here to here, and then we could use another neuron to map everything from like this value to the next value, and that will go up in some other direction using these transformations that we can use. Already you're getting to see how powerful this is. with a negative weight and this single neuron, the function has become a question of when this neuron deactivates. So it's actually a beautiful way of explaining it. Before we had at what value x will this function activate. Now we have at what value x will this function deactivate. Up to this point, you've seen how we can use the bias to offset the function horizontally and the weight to influence the slope of the activation. Moreover, we're also able to control whether the function is 1 for determining where the neuron activates or deactivates. What happens when we have, rather than just one neuron, a pair of neurons? For example, let's pretend that we have 2 hidden layers, 1 neuron each. Thinking back to y equals x activation, we unsurprisingly discovered that a linear activation function produces linear results no matter what. So even when we had multiple neurons back to back, you had a linear result no matter what. Let's see what happens with the rectified linear activation function, with the rectified linear function for the activation. We'll begin with the last values for the first neuron and a weight of 1. Sorry, hold on. We'll begin with the last values for the first neuron and a weight of 1 with a bias of 0 for the second neuron. So this was the same thing that we had last time, and now we have 1 and 0. We can see so far that there's no change. Oh, that's interesting. There's no change so far. This is because the second neuron's bias is doing no offsetting, and the second neuron's weight is just multiplying the output by 1, so there's no change. Like, this neuron is basically not doing anything. It's just multiplying the value by 1, so we're getting back the same thing, not adding any bias. So there is no change. Let's try to adjust the second neuron's bias now. Oh, this is going to be interesting. So now if we give the second neuron a bias of 1, whoosh, the entire function shoots up into the air. Isn't that beautiful? Now I encourage you, by the way, to try this. Let's plug in a value. Let's plug in, let's say 1. So 1 would be over here. So we'd expect a 0. Let's pass in a 1 over here, and we'd expect a 0. So 1 times negative 1 is negative 1. Negative 1 plus 0.5 is is negative 1 plus 0.5 is negative 0.5. Okay, is negative 0.5 below 0? Yes. So we're just going to return a 0. This neuron is returning a 0. When we pass in a 1, it returns a 0. Okay, now 0 times 1 is 0 times 1 is 0. 0 plus 1 is 1. And then 1 is 1 greater than 0? Yes. So let's return 1. Oh, and as you can see, when we put in 1, you get a 1 up here. So there will actually be no value that you could get a 0 here. Yeah, there is no, the y slope never actually intersects with the 0 axis. So that's interesting. But yeah, when you pass in a 1, you get a 1 as we expected. And I encourage you to plug in more values. Let's plug in 0, which we see should get you around 1.5. Let's try that. So 0 times negative 1 is just 0. 0 plus 0.5 is 0.5. Is 0.5 greater than 0? Like when I say the if question, that's the rectified linear activation function going. So is 1.5 greater than 0? Yes. So return not 1.5, 0.5. So this neuron will return a 0.5. 0.5 times 1 is 0.5. Okay, 0.5 plus 1 is 1.5. Is 1.5, again, this is the rectified linear activation function working, is 1.5 greater than 0? Yes. Return 1.5, and as you can see, we return a 1.5. And so you see, this is just beautiful, where it's like a floating thing, and we have this beautiful mapping. This is nonlinear. This looks very nonlinear to me. It's like flipped around, and it's hovering, and it's offset. It's like a bunch of transformations. Okay, now we see some fairly interesting behavior. The bias of the second neuron is indeed shifting the overall function, but rather than shifting it horizontally, it shifted the function vertically. It floated it in the air. What then might happen if we make that second neuron's weight -2 rather than 1? So now it's -2 for the second neuron's weight, and we get this beautiful thing. This kind of looks like the sigmoid activation function, and so you can really model anything with the rectified linear activation function. It's really cool. With just 2 neurons. So great. So this is the shape that we get out. Take my word for it. Or let's try plugging in some things. So let's plug in 0.5, and we should expect to get. I mean, we already did that. Let's plug in -1, and we should expect to get a 0. So -1 times -1 is 1. 1 plus 0.5 is 1.5. Is 1.5 greater than 0? Again, rectified linear right there. Is 1.5 greater than 0? Yes. Okay, so this neuron is going to return a 1.5. Great. 1.5 times -2. Well, what is that? That is -3. Yeah. Sorry. 1.5 times -2 is -3. Yeah. Great. -3 plus 1 is -2. Is -2 greater than 0? No. return 0, and as you can see, we do return a 0. And so just with this, we get this beautiful situation over here that returns a value between 0 and 1, which is kind of what we always wanted. We always dreamed of having a function that returned a value between 0 and 1. The difference is we're just using two neurons to do that, and you get that beautiful thing, that beautiful result. Great. Okay, something exciting has occurred. Great, now he's going to talk. What we have here is a neuron that has both an activation and a deactivation point. When both neurons are activated, when their area of effect comes into play, they produce values in the range of the granular variable and output. If any neuron in the pair is inactive, the pair will produce non-variable output. So basically we have this deactivation point from the first neuron, and we have this deactivation point from the second neuron. I believe that's this one. And so if this one if this neuron is going to return a 0, the whole thing will return a 0. If this one will return a 0, the whole thing will return a 0. And they'll return a 0 in other cases. Sometimes if they're both active, they have this area of effect, this area of activity being active. If the input is both in this area of effect, then you get this beautiful result, this beautiful line over here. And as you can see, he does use this like way of speaking with an area of effect. That's not exactly how I think about it, but it's how he thinks about it, and it works. So if you pass in a 2.5, 2.5 is within both of their areas of effect, and so you get back a 0.5. What is not both of their areas of effect? Well, -1 would be in this one's area of effect, I believe. Yeah, -1 would be in this one's area of effect, because as you can see, it goes up like this, I think. I don't know, maybe. So yeah, -1 would be within this one's area of effect, but it wouldn't be between in this one's area of effect, and so you'd get a value over here, and so you get a 0. The other way works too. 1 would be in this one's area of effect and not in this one's area of effect, and so you get a value of 0. But 0.25 is within both of their areas of effect, and so you got a 0.5. Great. Okay. So that is a basic understanding of how rectified linear works and why it's useful. Encourage you to go and watch his animation in his tutorial, because it's actually maybe it's going to be over here actually. I remember this. Yeah, he does this in the book. So he does this as an animation in the video, but he's going to show step by step in the book. I wonder if I should cover it or if it would just be a waste of time, because he really does show how you could use the rectified linear activation function and all these neurons to create this effect, to model the sine wave. I just wonder if... Here, animation for the entire... Okay, so instead of going through this in the page, let's take a look at the animation. Oh, no, I wanted to open that in a new tab, please. Can you please send me back to my PDF? Thank you. Open link in new tab. Great. Let's take a look at this animation. Again, this was made by him or by his friend, maybe. So credit to them. This is not mine. And go buy the book, essentially. Okay, so here we have... yeah, so he's just showing you how this works as a rectified linear. And again, these are the biases that we covered. Let's skip a little bit. And here we have these two. So as you can see, it needs to be in both of their areas of effect to work. And now it's not. Oh, so I got the neurons mixed up. So over here would be within this one's area of effect, but not within this one's area of effect. And so it doesn't activate, but it needs to be in both of their areas of effect. So now let's take a look at the entire neural network structure, but we're going to simplify it. Instead of it being fully connected, this one will be connected to this one connected to this one connected to this one. So you're losing a lot of data. Most of the time they're fully connected. Every single neuron is connected to every single other neuron, but for simplicity's sake, we're just going to pretend we're only going to work with these neurons, like them connected together. And we're going to try and model the sine wave. So we start out with just a simple thing. Everything is set to 0. And so we tweak the weights and biases of these first two to get it up here, and then we move this bias up so that we could bring it down, and then we bring this back down using another weight over here apparently. And so now we have a first chunk, and we could use these two to just bring it back up. And so he's going to be using these two neurons to like bring it back up. So the ones up here he'll use to model each slice, and things will like fall apart and you'll see problems occur. But now this is going to be the next slice. So you see we have this bend over here. You can only get that bend with the rectified linear activation function. You can only get that bend because there'll be an activation and deactivation point of these two neurons. And again, he's going to use these two neurons over here with this weight to just bring it back up. Okay, now onward with the next two, he's going to make another slice. Let's speed this up a little bit. And so again, he's tweaking the weights and biases over here to bring it up and down to get the next part correct, and then to bring this down. And there's no offsetting that needs to occur. Now he's going to get the next part, and he has to bring it all the way up and bring the thing down and change a whole lot of values. And this is actually the job of the optimizer. I believe his friend actually went in and tweaked these values by hand. So this is I believe his friend's name is Daniel, so it's the Daniel optimizer. I think that if you go into his video, he'll say the same thing. It's the Daniel optimizer, as opposed to, of course, the Adam optimizer. So again, we get this beautiful situation, and I want to reiterate that these bends only exist because of the rectified linear activation function. Now, it does look a little bit blocky. The reason why it's blocky is because we only have these connections, and we only have this many neurons. If we had all of the connections, it would be as smooth as you could possibly dream. And there you go. Using the rectified linear, we have all these area of effects that turn on and off depending on what the access is, and so you get the correct output for every single input, and it's just beautiful. I think it's absolutely beautiful. And yeah, so now he added all the other connections, and with all the other connections, we get a much smoother graph. So there you go. That is the rectified linear activation function. Okay. Let's take a look. Where are we? It should begin to make more sense now that it should begin to make more sense to you now how more neurons can enable more unique areas of effect. So each pair of neurons in that animation were responsible for a given area of effect in our overall sine function, right? So the more neurons you have, the more neuron pairs that you have, the more areas of effect that you can create, and so the more smooth it can look. And he shows this over here. When you have 64 by 64 neurons, you get an area where you get an emulation that looks like this. I guess emulation is an okay word, and it's very smooth. It's very nice. Okay. Okay, so now let's take a look at some code. Very exciting. We haven't been coding at all. So this is the rectified linear activation function code. Imagine over here you have this many inputs. The outputs would be an empty list. For I in inputs, if I is greater than 0, outputs.append I, else output.append 0, print output. And so this would be a very basic rectified linear activation function. So let's make this example. In our. Sorry. How do I? They're not split screen for some reason. Let's bring this back down. Okay. So let's make this exact example in our code. Let's comment out some of the code that we have here, main.go, and let's do this exactly. So, inputs, equals, make a slice of float 32 with a, how many of them will there be? 1, 2, 3, 4, 5, 6, 7, 8. Actually, you know what? I'm just gonna hard code it because I just realized that this won't work. Float 32. And this will be a slice, and then let's copy and paste these values. I get to copy and paste it because I have the book. If you want to copy and paste it, you should buy the book. And yeah, otherwise just hard code it. It's 0, 2, -1, 3.3, -2.7, 1.1, 2.2, and -100. Great. Those are our inputs. Now, outputs. I'm going to say outputs, equals make. And this one I will be using make syntax, make a slice of float 32s with a length of the with a size of the length of inputs. Great. Now, I still want these things up here. Please don't get rid of them. Thank you. Okay. For I equals the range of inputs. Val equals inputs. Actually, you know what? I'm just going to do for underscore comma val equals range of inputs. If val is greater than 0, then outputs index. I actually need the index now. Outputs index I. So I'm going to say for I comma val. Outputs index I equals val. Else. Outputs index I equals 0. Great. And now we can come down here, fmt.println outputs. And you don't have to import it again because we still have it over here. And actually, import. Please don't mess up my importing syntax Visual Studio Code. I need that. Great. Okay. Great. So now we could run this. Go run everything. And we get out 0, 2, 0, 3.3, 0, 1.1, 2.2, and 0, which is the same thing that he got out as well. So it's working. So that is basically, that is applying the rectified linear activation function on each one of these values in the end. That is basically what we're doing. Another way to do this is, instead of doing it with the if statement, we can simply say we can simply do the max. So instead of doing this if statement, the max between 0 and the value I, and the value at index I. So we can say outputs index I equals math dot max, max float 32, I guess, between 0 and val, right? What's wrong here? In val operation, can I call non-function math float 32 untyped constant? Oh, sorry, this is not a function. How do you get max? Yeah, it's just, there you go, max of, math.max of, and this needs to be float 64, so let's change both of these to float 64s. Float 64 and float 64, great. Okay, so I'll put it between 0 and val. So math.max between 0 and val. This will return the same result, except no if statements, because the if statements are being handled by Golang. Yep, exact same thing. Excellent, great. But a much cleaner code. So basically, this is a rectified, not even this. This is a rectified linear activation function, the maximum between 0 and the value. Okay. So NumPy, he's using NumPy, has basically the equivalent. It could take in a NumPy array and return the maximum between 0 and the inputs, which is very useful for him, because he has that. We're going to have to figure out how to do this with tensors. So let's figure this out. So let's figure this out for our library where we're using tensors, because I don't actually know how to do this yet. So that's going to be interesting. I need tensor, please. So I need this package. Gorgonia.org/tensor. The link will be in the description. So I need that. And I'm going to say inputs doesn't equal that. I'll say inputs backing is that. So the input backing will be that. And instead now inputs colon equals t.new. And this will be t dot with backing of inputs backing. Great. So now we have a tensor for our inputs, and I bet it has something similar to this. So instead of doing it like this, instead of having a for loop, we'll simply say outputs colon equals t dot max. I'm sure there's a max. This is softmax, which is an activation function, actually. Max between, maybe? We'll do something. I don't know. I didn't actually look into this. Is there a rectified linear? No, there is no rectified linear. We have to figure out how to create a rectified linear situation for our tensor objects. And I didn't actually look into that, which is a mistake. I should have. So let's take a look at this. Tensor. Max. Functions. I need something in functions, I guess. Max int. Maybe this will do it. Max int returns the maximum of a slice of ints. No, that's not what I want. Okay, there might be something that we can use in the actual inputs class. Hold on, what did I just do? Sorry. Did I mess something up here? I have no idea. So how about instead we'll say inputs dot, maybe there's something here, max. No. No, none of these work. wonder. Does not look like there is anything. That is unfortunate. we may have to like hard code it in a way that will not be ideal. We may have to do that. Yeah, this could be a problem. This could be a problem. Okay. First thing I want to do, I think we're gonna have to do this. So first thing I want to do is I want to see if we can iterate over a tensor. So for I comma val colon equals range of inputs. Does this work? No. No, it does not. Cannot range over inputs. I have type. Okay, so how about inputs dot raw? Does that work? Yes. Yes. fmt dot println I comma val. So let's see if this works. Go run. And 0, 0, 1, 2. Okay. How about just give me the value? And like this. Okay, so this is clearly not what we have. Can we turn this into a float? Float 64 of val. Maybe. No, same thing. Okay, so that didn't work. Inputs dot. Yeah, float 64s. That's exactly what I wanted. Okay. And this will. Yeah, this gives the exact appropriate thing. We don't even have to cast it to a float 64. Okay, great. So we're gonna have to hard code it. We can't really use a NumPy thing, so we're gonna have to. Yep, we're gonna have to figure it out. So over here, he uses the NumPy.maximum. We're gonna have to do something different. So he actually makes a class called the rectified linear class. It basically has a forward pass, and it sets the output to be the maximum between 0 and the inputs using NumPy. Great. So we're gonna have to make something similar. We'll make a struct. So it's called an activation function, but he makes it into a class. Should we make it an activation function or should we make it a class? I feel like we should just make it a function. I don't know why he made it a class. Maybe because he wants everything to be classes. Fine, we'll follow his lead. We'll do it like that, and then he applies it to his situation, and he gets that. So I think that we'll go up until here. Yeah. We'll talk about the softmax activation function tomorrow. So let's do exactly this. So let's make the struct. So let's come back into the code. And let's go into our machine learning package over here. We'll make a new file. We'll call this file actually activations.go. Here we'll put in all the activation functions or structs that we're going to use. So let's make a new, we'll make a new type, and it will be activation ReLU, similar to how he called it, and this will be a struct. And this will have well, it will only have actually one attribute. It will have a output, which will be of type t dot, and we actually need the tensor package now. Oh, sorry, we need to call this a package. Package ML. Great. And import t, which is going to be gorgonia.org /tensor. Great. Okay, so output is going to be of type t dot tensor. Okay. Great, and now we'll make a function. So func let's do this R, and this will be star activation ReLU. This will be forward. Yeah, I mean, just for consistency's sake, we should probably make a function to get a new activation ReLU. So func. Oh, that's interesting. Oh, that's interesting. No, it's not interesting. Never mind. Func new activation ReLU. Yeah, and this will return a, yeah, this will return a activation ReLU, and it will simply return activation return activation ReLU, and the output will just be t.new. And we don't have to put anything here, it'll just be an empty tensor for now. Yep, that'll just be the raw activation ReLU. And now let's make the forward pass. That's not how you spell forward. Great. And this should be uppercase over here. Output, and this should also be uppercase. Great. And this should also be uppercase. My God. Okay, now let's actually program this in. So, the forward pass will take in inputs, which will be of type t.tensor. And we're going to have to iterate through it. So, for I, comma, val, colon equals, hold on, give me a second. For I, comma, val, colon equals inputs dot float. Colon equals range of inputs dot, not shape, but dot float. What's wrong here? Can I not do this? Am I not allowed to do this? Oh no! I thought that we did have this. Oh no! What's wrong? This had this. Why did this have this? It's a t.dense. T.dense? Tensor. What is this? Float 64 z. There's an S over here. What? No, nope, doesn't exist. Excuse me. Okay, that could be problematic. Okay, for now we'll just set this to be t.dense, and if we run into problems we'll have to fix that. But great, for now this is gonna work, I think. Now we say, I don't think you'll ever have like multi-dimensional inputs into the activation ReLU. I mean, no, you will, because we're working with batches. Ooh, that's gonna be problematic. Oh, that's gonna be very problematic. Okay, yeah, this is gonna be problematic. We'll have to fix this later, but for now, let's just get this working the way we want it for now. Okay. Okay. Great. Terrible. I'm just anticipating like terror. Okay. Let's say output backing colon equals a let's say make of type, it's gonna be a slice of float 64s with a size of with a slice of inputs dot size dot data size. Yeah, sure. The built-in function that allocates the initialized an object of type slice, map, or chan. Like new, the first argument is a type, not a value. Sorry, no, that's not what I want. I want document data slice returns the size of the underlying array. Typically, t.data size equals t.shape dot total size. Great. Okay. So yeah, we want the data size. I wish there was a way to get something here. Strides. What's this? No, I don't think that's what we want. Dot. Apply clone. No, shame. Okay, fine. So this is gonna have to be a dense. We'll have to figure out a workaround. I'll do some research and figure out a workaround for next time, whenever we run into a problem. But okay, for now this is gonna work. So now we have this. Yeah. So now output backing index I equals math dot max between value and 0. Great. And now, so great. So this was the output backing. And now we'll say that r dot output equals t dot new t dot with shape, and so this needs the shape of inputs dot shape. Great. And then this needs t dot with backing of output backing. Hold on, let's collapse this for a second. With backing of output backing. And if you know anything, if you've been following along with the tutorials, this is basically how we use the tensor library. We populate a slice with the appropriate values. We get the shape for our tensor, which will be the same shape as the inputs for now, which is just going to be, unfortunately, it's going to have to just be a one-dimensional thing for now. We'll have to figure out a workaround for that. And then we'll say t dot with backing, output backing. And so we populate this new output, which will be of type tensor, in a output backing in a tensor format using output backing, which was the slice that we made and populated accordingly. And so here we have the rectified linear activation function forward method, similar to how he has it over here. Okay. Now he wants to apply this activation function to the dense layer's output in our code. So before we had this x and y, the dense layer 1, so he's going to make activation 1 and dense 1 dot forward, activation 1 dot forward, and then, yeah, okay, so let's put that into our code. So he's only using the first two dense layers, so let's do that. Let's make the dense layer 1. So here we have a dense 1, which will be ML. We need to import ML up here, which is our machine learning package, by the way. We could get rid of this example over here. We don't really need that. And over here, we'll also have activation 1 colon equals a new ml.new activation ReLU, and then we'll say this is we're already going to run into the problem, I think, but let's see actually, maybe we won't, dense 1 dot forward on x. Where is x? X is in another file that we have over here, data.go. Watch a separate video to see how we created that data and how we got into tensor format. So, okay, so back over here, dense 1 dot forward x, and then let's say activation 1 dot forward dense 1 dot output. And this will throw an error because this is of type tensor, and we need of type tens. So let's see actually if we could do yeah, no, this is gonna be, yeah, this is problematic. This is problematic. So for now, instead of passing an x over here, let's just pass in, here, we can say input colon equals t dot new, we need t over here, we need like our tensor package, tensor package. So t dot new, what's wrong? This is good. Stop complaining. Undeclared name. It is declared. What are you talking about? Unbelievable. Sometimes it has so much trouble finding stuff. T dot, thank you, new, great. T dot with backing, and let's just make a random slice over here. Let's say like 1, -2, 3, great. And now over here we can come over here and we'll say of inputs. And we can come over here. Oh no, this is still of type layer dense. Output. Yeah. Okay. You know what? How about we just pass in inputs here for now into our activation 1? And why is this a star? Okay, and let's try and run it. Oh, and we're not going to print anything. Oh, and there's an error too. Invalid memory address for nil points. For nil pointer dereference. What? So fine. So in the activations, we'll take in a pointer to dense, I guess. Over here, we can go like that. Maybe this will work. No, there's still problems. Okay, you know what? I'm going to do some research. I'm going to figure out how to code the forward method for the activation ReLU properly. Until then, yeah, take care. We've learned a lot, and I'll see you guys in the next one. So yeah, that's it for today. We've learned a lot about activation functions, how to use them. Sorry we couldn't code one, but I thought that I would know how to do it, and then it came time to do it, and I did not know how to do it, as very often happens in coding. So I'll figure this out, and I'll see you guys in the next one. probably tomorrow. Any questions you have, leave it down below. Check out the book. Hope you guys enjoyed. Check out the full playlist if you want to. And yeah, I'll see you guys in the next one.